Okay, so last time we finished chapter 1, which was Introduction to Earthquake, and we briefly started chapter 2, Theory of Vibration. We'll go through it quickly as a revision, and we'll proceed from where we stopped. So we did go through some definitions of vibration and terminologies. Vibration can be anything, any back and forth motion, like a pendulum motion with kinetic energy and potential energy continuously changing, or it can be a foundation vibration caused by a motor sitting on a foundation, or it can be caused by also like an earthquake from ground vibration, or anything else. It can be a car vibration or a wind vibration. These are just few examples. And you can have a periodic motion, a motion which repeats itself in a regular interval of time. And a harmonic motion is a motion which can be represented by a sine or cosine function or a combination of the two. And non-periodic motion is a motion that doesn't repeat itself. It's kind of irregular. And period and frequency, these are the most frequent terms we'll be talking in this section. And period is, it's if everything vibrates back and forth, then the time it takes for one complete cycle, we define this as a period. So that's called a natural period. And every object, every building, every structure has its own natural period. If you give it a free vibration, there is a time period it takes for one complete motion. And the unit is second. Sometimes it's confusing with a time period when we put it, but when we say a period, it's for one cycle of vibration. And frequency is just the inverse of period. Or it tells us how often the cycles are repeating. You can have a motion with a high frequency or low frequency depending on how many cycles you have. And we also discussed damping. Damping is just a doubt of energy. Energy dissipates at some point. We'll discuss a detail on damping in the follow-up chapters. We'll divide it into two: viscous damping and also radiation damping. The viscous is when we say it's just a material damping. Particles are rearranging or deforming, and a friction loss between particles. That's what we call viscous damping. Radiation is when you have, depending on the geometry, reflection and refraction of the wave itself, and depending on how wide your medium is. So Alex is on the radiation damping. Anamut, welcome to the class, Anamut. So we'll discuss your question at the end of the class. And degree of freedom is the number of independent coordinate systems that you need to completely describe the motion of an object. You can have 1 degree of freedom system, 2 degree of freedom system, and even more. To completely describe a solid object or a rigid system, you can have 60 degree of freedom system, 3 rotation and 3 translation. And we also discussed the spring mass dampers model. This is a simplified way of representing such as a soil mass or any object, where the spring represents the elastic nature of the soil and the damping represents the dissipation of energy. Somehow if you apply a force at the top, that force dissipates with depth. Because particles rearrange, there is a friction loss between particles, and so many things like that. So that dissipation of energy we represent by a dashpot. And then the spring is the elastic response of the soil. And the mass is the mass of the foundation block, and any like if you have a motor vibration at the top, the mass of the motor at the top. So more examples of single degree of freedom system and multi-degree of freedom system. You can have a building with multi-degree of freedom system. In this simple example, you have just 3 degree of freedom system, the entire story lumped as 3 masses with stories. But if you model this in structural software like SAP or StatPro, you can have thousands of multi-degree of freedom system. It's just an example how you can model it. Okay, I think we covered last class until this point. And this section is a general equation of motion for externally applied force. So if you see an object like a mass where we're applying an external force P to the right, if you see this P applied force, then you have, let's assume the floor it is sitting is frictionless. So there is no force of resistance at this point. Now, the force of resistance is, let's say you have a spring and a damper. This is just a simple example how we modeled our foundation block. You have the soil represented by elastic spring and the dissipation of energy by the damper. And you have a mass and you have some kind of force. It can be a static force or it can be a dynamic force. So if you draw the free body diagram of this mass, you have a force, a mass, a damping force, and a stiffness force. And also you have inertial force acting on it. So if you apply Newton's second law, which says for a mass where it is subjected with a force, you have equivalent inertial force acting in the opposite direction on the mass itself. And also you have a resistance because it's sitting on something or it's attached to something with a damper and a stiffness. So if you find the equilibrium of these equations, you have applied force minus damping force minus stiffness force minus the inertial force equals to 0. Everything has to be 0. So in the end, what you'll have is the inertial force plus damping force plus stiffness force equals to the applied force. So this is the general equation of motion, no matter what system you are analyzing, whether it is a geotechnical system, structural system, mechanical system, the general equation of motion remains the same. You always have inertial force. Inertial force is the mass times the acceleration of the object. Acceleration here we represent this as u dot dot. It's the second derivative of displacement. First derivative of displacement is velocity. Second derivative of displacement is acceleration. So for this class, acceleration we represent it by u dot dot. And the second force is a damping force. The damping force is proportional to the velocity of that object. So it's a damping constant times the velocity. Velocity is first derivative of the displacement. And the stiffness force. Sometimes you may have a constant force acting on it, or a vibrating force acting on it, or only maybe in some cases just initial force. And with some disturbance, there is no constant force applying on the object. So in that case, it can be 0. You can arrive to the same equation of motion using D'Alembert's principle. D'Alembert's principle, it says, for any object in motion, the externally applied forces, inertial forces, and force of resistance form a system of force in equilibrium. It's basically very similar to what Newton's second law is. So you have all your forces, externally applied force, inertial force, and force of resistances from damping and stiffness. So we are doing this equilibrium in the horizontal direction. But if you take it also in the vertical direction, there is no vibration, but there is a gravity downward and reaction from the floor. So either in the vertical or horizontal direction should be in equilibrium. So for a static problem, the velocity and acceleration of the mass are negligible. So everything is in motion. That's very clear. The Earth is in motion around its own axis. It's always rotating. Also, the Earth is
ሄሎ
rotating
ዶክተር
around the sun.
ሄሎ ዶክተር
Yes, I hear you.
ይቅርታ መብራት ጠፍቶብናል ግቢ ያለን ልጆች
Okay. So what should we do? Are you able to follow me?
አይ አሁን በዳታ ነው እኔ የገባሁት ሁላችንም አንድ 6 ተማሪ ውጭ ነው ያለነው አብረን ያለን
Okay, let's stop recording and let's see.